Okay. So for today, what we're going to take a look at, we're going to look at, instead of infinite limits, what if we moved and got x out towards infinity, like far, far away from the origin? So let's take a look at a picture and see what, what's this nonsense that Mr. Joyce, he said infinity, I'm just going to go to sleep type of thing. Let's take a look at the picture for this first graph. So it's y equals, and of course, I would do this in your TI-83 as well if you're following along. X squared plus 1. So let's take a look and see what this picture looks like. So there's some kind of a strange behavior. It does some weird stuff in the middle, but you notice it kind of calms down at the ends. The ends kind of smooth out, and the ends sort of, they actually make an asymptote there. And that's what we're going to be working on today, is as we zoom out, let's go even further. Let's go like -20 to 20. That keeps, there's no more craziness in the graph. It looks like it's approaching the number 3. Right? And we want to figure out, how do we predict this ahead of time, or how do we recognize where this behavior occurs on a graph? Okay. So if we keep the, you can see the picture there. Hopefully you've got something like that in your calculator to look at. If we were to take a look as x goes to infinity, then that picture is the right side of the graph, the far, far right side. That value is approaching 3 over on this side. Okay. So for now, we're not going to do anything rigorous. You can take my word for it that as you go to infinity, it is approaching 3. As we went to the left side of the graph at negative infinity, the same thing was happening. It was approaching the number 3. Okay. So limits give us a way to find horizontal asymptotes, and we can do that using the idea that if we take the limit as x goes to infinity of f of x exists, and of course it could be in the other direction as well, then f of x has an asymptote that is the value of the limit. So I didn't plan that very well, but I'll write it over here. I'll say then f of x has a horizontal asymptote equal to the value of the limit. So I'll put, just to show you again on that picture then, here's the graph. If I put in y equals 3, there's that asymptote. It's showing it's just approaching the number 3. It's just sneaking up and just getting real close, like you're used to seeing with a vertical asymptote. Okay. So since we're working with infinity, we should probably discuss some things that may occur to us. For example, what do you think happens in this first limit? If I have a constant, so any real number, could be like 2, -5, square root 7, any real number, what do you think is going to happen as I go towards infinity for some polynomial? Is it too early to talk about infinity?
Possibly.
Possibly. There's probably a good chance that it's too early. Well, I mean, you can always think about that table of values was one of our first ideas. What if it was the number 5 and you were dividing it by 100? And then 5 divided by 1,000? And then 5 divided by, and we keep going. What do you think that limit is going to be approaching?
8.
0 is correct, yeah. So it's going to be approaching 0 because the bottom gets so big that it overpowers the top, and that limit is 0. Now, even if we go to negative infinity, it's still going to approach 0. It's just going to do it from the bottom. So what I mean is, there's no such thing as -0 or +0. It's going to go to the same place. It'll just, instead of coming down from the top of the graph, it will come up from the bottom of the graph. Okay, and of course, if we take some constant and we raise it to an infinite amount, then this is going to, we can't, there's no number that converges there. That's going to disappear. But if I move towards negative infinity, then this is going to end up going to, what do you think? Yeah, 0. How did you know 0? Yeah, it's going to make it, that flips it, makes it a 1 over. That's the same thing as the limit as x goes to positive infinity of 1 over c to the x. So that'll be 1 over some infinite number. So we'd be going towards 0. Okay, so let's see if we can find some horizontal asymptotes from these first couple of limits. So what do you think the horizontal asymptote is going to be as I approach infinity for 5 minus 2 over x squared? Yeah, Danny? How'd you know it was 5?
Because you do a similar denominator thing. So it's 5x squared minus 2 over x squared. And then after, so this turns to 5.
Okay. You actually don't need to do the common denominator for it. That would be fine. I guess it would help in the graph. But in this case, really what you're looking at is two limits. Okay. This is a constant, so that limit's simple, right? It's just 5. This one here we just talked about, that's that one. So what we're doing here is we're going to say this limit's going to 0. So 5 minus 0. If you were to graph this, there would be a horizontal asymptote at 5. Now, what do you think? Is there an asymptote we can find for the next one?
0. Yeah,
you're right. So the bottom of this just keeps growing wildly larger as x gets bigger. So this one, we'll be talking about it approaching 0. Yes?
So whenever there's an exponent on the bottom, is it always going to be 0?
Well, when x is going towards infinity, then that's probably the case. But we can mess around. We could have negative x's that move things up and down. But I guess in the simplest case, yeah, if x is going to infinity, if it's like x cubed, x squared, it's going to be going to 0. Okay. Okay, so this is the limit we've already been talking about so far. When I was saying, you're not allowed to give up and just say there's probably no limit. When you have 0 over 0, that's the one we were looking at previously. Now we're going to take a look at infinity divided by infinity, which again is an interesting limit because, infinity is more of a concept. It's not really a number, right? So what happens when you divide to...
Imaginary number?
It's not a number, right? Infinity is like, okay, look, you see the number line at the front of the class? If I said go to 40, you could actually walk to 40 and stand there. If I said go to infinity, you just keep walking. There's no place that you go to. There's no number that you go to.
If there was a place.
Well, if there was a place, then I guess we call it infinity. Anyways, that's people always have trouble with infinity, right? It's not actually a number, but it's actually a...
So it's an imaginary number.
Okay, then we'll stick with that then. Okay, we'll call it... But you have to be careful because an imaginary number is like, we usually call those the square root of negative numbers. That's the only reason you wouldn't say it's imaginary, because we already have a group of imaginary numbers. Anyway, we can move on. So
classify them into 2 different groups.
I don't know, maybe that could be a project, a PhD for you to work on. Yeah? There's lots of PhDs with infinities, but anyway. Okay, so we're taking a look this time. I'm showing you an example here. This is the function that we're looking at, and here's its graph that you have in front of you. Now, this is the asymptote that's been graphed, y equals 5/3. Okay. So I can see that as I approach this way, I'm going towards infinity, that I'm hitting that line 5/3, and as I'm going on the left side, I keep getting larger and larger negatives. I would still be touching the asymptote 5 out of 3. Can anybody figure out maybe how we could start predicting this? Like, what's special about 5/3? Is that just thrown out there as a random, it just so happens that it's 5/3? You're on fire today, Danny. Go for it.
Okay, it's the coefficient of the largest x power.
Yeah, so if you look, here's 5/3 showing up in our problem. Okay, so we'll talk about why that is. I think I'm going to the next part here. Okay. Okay, so I call this the Bill Gates theorem of calculus. And I don't know if it was this block or, I think it was the other block. I said, okay, if you had $1 trillion and somebody dropped a nickel, would you pick it up? And they all said, yes, of course I would. And the reality is, if you were that filthy, stinking rich, you probably wouldn't care about a nickel. But this is, so the only person I can say, well, I mean, there's more than, there's Warren Buffett. There's other people that are very, very rich. But, for Bill Gates, he has so much money that you think, well, what if his annual salary was increased by $1? Woohoo! Do you think Bill is going to jump and do a dance for us? Probably not. That dollar is really insignificant as those numbers get bigger and bigger and bigger, right? However, if you were in the unfortunate incidents where you were homeless and someone threw $1 in your hat, you'd be pretty excited to go out and get yourself like a McDonald's cheeseburger or something like that? Or a chocolate bar, right? You'd be pretty happy because that made a big difference. But as those numbers get larger, things like ones, they're insignificant. So that's why when we had that previous example, as we get really big, slow today. Bill Gates needs to make his computers faster, I guess. As we get bigger and bigger, it's these things here which become insignificant, right? It's weird to think, well, how do we just throw those values out? They actually add something to the graph. And the answer is, yeah, of course they add something to the graph. But the bigger and bigger we get, the less significant those terms become. And that's why they tend to sort of wash away into the, we can almost consider them being not there at all. Okay, that's why 5/3 pops up.